Okay, in this video I want to discuss average rates of change or instantaneous rates of change. This conversation is going to lead us to ultimately a conversation of derivatives. So this is sort of an introductory chapter into the concept of a rate of change, and we're going to frame this around a word problem, and then we're going to focus kind of numerically how we would make these calculations. And a little bit later, what we'll do is focus a little bit more algebraically to make our life a little bit more efficient. All right, so to add a little bit of context to what we're doing here, what I want to do is throw out a kind of simplistic situation where we are sitting in a tree and we're dropping an object out of the tree. So let's suppose that we are sitting in a tree and we're going to graph this scenario, right? So let's say here's a graph and we're looking over time at the height of the object that we're dropping. So let's say that, let me switch color, let's say that the tree is 16 feet tall, right? And we're going to drop the object and it's going to fall in a parabolic path and it's going to hit the ground. Right? So let's say that the height of the object is being described as a function of time, and we have 16 minus t squared, right? So let's say this quadratic function, this parabola, models the path of the object as a function of time. Now we know pretty simply, right, the equation that I picked or tried to make it as pretty as possible. We know that it's going to hit the ground at 4 seconds, right? That's the x-intercept or the t-intercept in this case. So let's say you have 1, 2, 3, and 4, and the tree was 16 feet tall. So when we initially release, right, when we initially release at 0 seconds, the tree is 16 feet tall. So the object is going to fall in this parabolic path. So let's say what we want to do is find the velocity or the speed at which this object, let's say we're dropping a stick, right? So we're dropping a stick out of the tree, and we want to determine what the velocity is or the speed the object hits the ground. So here's going to be our approach. And so most likely, in a pre-calculus course or an algebra class, you have learned about an average rate of change. And what you discuss is that a line has a constant average rate of change. So in other words, if I come over here and draw a quick line, right, here's a line. So if we talk about the slope of this line, the slope is the same between any 2 points. So if I pick this point and this point, the slope is the same. If I pick this point and this point, the slope is the same. If I look between these 2 points here, the slope is the same. So we attach the terminology in a pre-calculus course that rate of change, that slope, is constant. So the rate of change doesn't vary at all. If we look over this parabola for a moment, let's say I plot this point to this point, right? There's going to be a rate of change that looks kind of flat here, almost zero slope, right? Almost horizontal. And then if we look at the rate of change down here, we have a pretty steep line between those 2 points. So for any graph that's nonlinear, we have a rate of change that is varying. Right? So again, for a linear function, we have a rate of change that's constant. For a nonlinear function, we have a rate of change that is variable. So what we're trying to do really is find the slope of the line on the parabola. We're trying to find the slope of the parabola when it hits the ground. We don't have the tools by which we can do that yet at this point. So in order to accomplish the task of finding the speed at which the stick that I've dropped hits the ground, we're going to do some estimations. And what I want to do is take a couple different steps here, and let's build our way up to ultimately what we're calculating, right? So let's take a really gross estimate, and let's say between 4 and 1 second. So we're going to find the average speed between 1 and 4 seconds. Let me just change colors so we can kind of make a visual distinction. So to find the average speed, in essence, what we're doing is we're estimating what the function looks like with a line. It's not the prettiest of lines, all right? So there's what we would call a secant line, really. And that's some of the new terminology that we will use within a calculus course. So our average velocity or our average speed, I'm going to say V average, that's really the slope of that line, right? It's the slope of the secant line is what we call that, right? And line that touches a graph at 2 points is called a secant line. So we're going to find the slope of that secant line. So keep in mind the slope of any line is, change in y over change in x. We could write y2 minus y1 over x2 minus x1, right? But in this particular case, right, we have heights, if you will, right? So we have height 2 minus height 1 over time 2 minus time 1. And I'm going to get lazy again and just say delta h over delta t, right? Those are the variables that we're looking at within this particular application of this branch, the stick that I've dropped out of my tree. Now, for this particular scenario, right, then we need the 2 points on that line, right? So if I take t equals 1 right here to find that point, I plug it in this equation. 16 minus 1 squared is 15. So I know that this is t equals 1, height is 15. And then obviously we can see here that when t is 4, the height is 0. So we're going to find the change in height over the change in time, right? So our average velocity in this case, so I have 0 minus 15 will be my change in height, and then my change in time will be 4 minus 1. And so we get negative 15 fourths. So we could write that as a decimal. Let's leave it exact just for the moment. And then the units on this measurement, keep in mind the units of the numerator, right? Those are our heights. And I've said verbally that those would be feet. And then the denominator, my change in time, is in seconds. So what we have here is our average speed or our average velocity, 15 over 4 feet per second. And as a decimal, that would be like, well, probably 3.8-ish, something along those lines. So I have negative 3.8-ish feet per second as our average speed from 1 to 4 seconds. Okay? And we're looking over that time interval, right? So again, I have an average, I'm going to be lazy here, an average velocity from 1 to 4 seconds is negative 15 fourths feet per second. All right, now what I had initially mentioned is that what we want to do is find the speed of the object, of our stick, when it hits the ground. So what we're going to do is let's shorten the time interval. So in other words, instead of going from 1 to 4 seconds, which you can see is not the best estimation of the Kirby parabola, let's go from 2 to 4 seconds. And let me switch colors here. And let's say I go from 2 to 4 seconds. So I'm looking at this point now to here. And if we draw a line, I'm going to do my best. If we draw a line connecting those 2 points, we can see that that line is a little better estimate of the curve, right? We can see it looks like the line hugs the curve a little bit better. So when we find the average speed over that time interval, it should be a little better estimate of the speed when it hits 4 seconds. So I'm going to have to scroll down here to give myself a little bit of room on my digital paper here. So what we're going to do now, right, we're going to find the average velocity, let's say, from 2 to 4 seconds. And again, remember, that's really just the slope of the secant line, right? It's the slope of our secant line. Now, for this particular example, right, the slopes have particular measures of unit, right? So I'm going to write this just a little bit different. So it's going to be the height at the final value, right, minus the height at our initial value. So we're looking from 2 to 4 seconds, and then we're looking over 4 minus 2 seconds. So when I plug 4 into my equation, again, I'm going to be getting 0. And when I plug 2 into my equation, I'm going to have 16 minus 2 squared. So 16 minus 4 is 12. And then 4 minus 2 is 2. And in this case, 12 over 2 is 6. So we're getting negative 6 feet per second. So the average speed, average velocity from 2 to 4 seconds is negative 6 feet per second. Now again, here's what we're going to do. We're going to make our estimate a little bit more precise. So I got to scroll back up here. Let me actually zoom out. See if this makes it a little easier, and then we'll zoom back in. Right? So visually what we've done, right, is we have found the average speed, the average velocity from 1 to 4 seconds. That's the slope of our green secant line. And then we have found the average speed and the average velocity from 2 to 4 seconds, right? And that was our red secant line. So now let's get a little more accurate than that. Let's find the velocity from 3 to 4 seconds. Right? So we're going to go from 3 to 4 seconds here. So if I plot the point at 3 and then the point at 4, if I draw a line between those two, notice that the line and the parabola are almost indistinguishable. So when we're finding the slope of the line from 3 to 4, we're finding with decent accuracy the slope of the parabola from 3 to 4. So our average speed, our average velocity is getting a little bit more precise in relation to the curve. All right, so let me scroll down here then, and let's say we're going to be finding our average. So we're going to have the average velocity from 3 to 4 seconds. Right, and again, I'm going to say, remind us, that's the slope of that secant line that we draw. So again, the slope of this line, right, we're looking at, the change in height over the change in time, and we're looking from 4 to 3 seconds. So here's our rise, if you will, our change in height, and then here's our change in time. So again, if I plug 4 into that equation, we have the height of 0, and if I plug 9 into that equation, we get 16 minus, I plug 3 into that equation, we get 16 minus 3 squared, so we get 16 minus 9, which is 7 over 1. So we're getting -7 feet per second for that scenario. Okay, so let's go ahead and then kind of organize this information in a little bit more of a precise manner. So I want to write a table, and so that we can organize this data a little more clean. All right, and so when I construct this table, I'm going to make this a little bit more long-winded than it really needs to be, just so we can have a conversation about a couple things at the end. So to fill in my table, right, let's say we're going to look at our interval. And so what I mean by that is in our first problem, our interval was from 1 to 4 seconds, right? So when we found the slope of that line, there was a couple things that we did. The first thing we did was we found the rise, right? So let's say we're going to find our delta H. And then, I don't know if I'm going to have enough room here. Let me scoot this over a little bit. So we're going to have our delta H, and then we're going to find our delta T, right? So we're going to find the change in height was our numerator of our slope, the change in time was the denominator of our slope, and then we're going to go ahead and find the average of the two. So for this particular problem, that was delta H over delta T. And again, I'm going to put the data in here that we've already calculated. All right, so from 1 to 4, let me scroll back up here because I forgot already. From 1 to 4 seconds, we had a rise. What was that value? We had a rise. Here was the 1 to 4 seconds that we did. We had a rise of -15. We had a run of 4. So we got -15 fourths for that calculation. And in this case, again, our units are feet per second when we're looking at this application. Now the x interval of time we did was from 2 to 4 seconds. So our rise from 2 to 4 seconds, I'm getting old and forgetful, right? From 2 to 4 seconds we found a rise or a fall of -12, and then our change in time was 2. So we had -12 as our rise, or our fall, right? Change in time was 2, and so we had -6 feet per second. Then the next value we had, let me continue on here. So we had the interval from 3 to 4 seconds. So from 3 to 4 seconds, right, we had up here, we can see from 3 to 4 seconds, we had 0 minus 7, which was negative 7, and 4 minus 3, which was 1, and we ended up with negative 7 feet per second. So what I'm going to do in this case is let's get closer and closer. So I'm going to come back up real quick just because I can't see it in the screen. I want to let these 2 points keep getting closer and closer together. So instead of looking from 1 to 4 and then 2 to 4 and 3 to 4, let's continue. Let's go 3.5 to 4, then we can go 3.9 to 4, 3.99 to 4, and let's let those 2 points get really close together. So I want to organize all this in a table just so it looks a little bit prettier. So if we go from 3.5 to 4, keep in mind what we're doing here is we're finding the height at 4 seconds minus the height at 3.5. I'm going to be dealing with some decimals here. So I'm going to go ahead and take out my calculator, find out what those values are here in a second, and then we're going to have the change in time, 4 minus 3.5. So obviously that's going to be 0.5. And let's go ahead and take out a calculator to find what these other values are. Right, so again, we're plugging this into our equation, right? So if we have 4 plugged into our equation, right, that's our x-intercept, and that was a height of 0. And then if I plug 3.5 into the equation, we have 16 minus 3.5 squared, and that's giving me 3.75. So my rise is 3.75, and that's a negative calculation, over the change in time of 0.5. If I plug that into my calculator, I'm going to get negative 7.5. So we have negative 7.5 feet per second at that point. So let's make the time interval even smaller. So let's go from 3.9 to 4 seconds. And again, I'm going to jump over here real quick, right? My change in time, is 4 minus 3.9, and that's going to be 0.1, obviously. And then what we're going to do is take the change in height. Again, I'm going to plug this into a calculator and find out what that value is. So that's going to be 0 minus, I'm getting 0.79 here. So my slope of my secant line, right, my rise over run, I have the negative 0.79. I'm going to divide by 0.1, and what that's going to give me as a decimal form is negative 7.9 feet per second. Now let's go ahead and do one more interval closer. Let's actually do 2. So I'm going to go ahead then and look at the points where I go from 3.99 to 4. So if I go 3.99 to 4, again, the change in time that I have here is going to be 4 minus 3.99, and that's 0.01. And then my change in height, right, is going to be the height between 4 seconds and 3.99 seconds. Again, plugging that into a calculator, I get negative 0.0799, and taking negative 0.0799 dividing by 0.01, we're going to get negative 7.99 feet per second. I think we could kind of see a pattern happening here, right? If we do one more, let's say we go from 3.999 to 4 seconds. What are we going to get in that case? Plugging that into the calculator, I'm going to get negative 0.00, negative 0.007999, and then I have 0.001 as my change in time. And when I divide those, I'm going to get negative 7.999 feet per second. So let's remind ourselves, what we're doing here visually. So we had our parabola. We had 16 minus t squared. So we had a value of 4 and 16 here. And we went from 1 to 4 seconds. So we went from 1 to 4. And then we went from 2 to 4 seconds. And then we went from 3 to 4 seconds. And then we did 3.5 to 4, we did 3.9 to 4, 3.99 to 4, 3.999 to 4. Now again, if I draw a tangent line, excuse me, a secant line between each of these points. It's going to get a little cluttered. We can see as the points get closer and closer, they estimate the curve much better and better. So if I look at these 2 points here, they're almost right next to each other. They're super, super close. So that is showing me, in essence, what the slope of the parabola would be if I got to 4. Now think about this for a second, right? If we go from 4 to 4 seconds, what's going to happen? If we go from 4 to 4 seconds, we're going to end up with, h at 4 minus h at 4. And that's going to give me 0. We're going to have 4 minus 4, which is 0. And we're going to get 0 over 0, which technically is undefined. However, when we look visually at this graph, we know right at 4 seconds there is slope. The slope is measurable right at 4 seconds. However, what's happening, right, is the denominator is becoming 0, right, when we do that. So this is the process that we would call a limit process, which we'll get a little bit more detail into the next value. So the reason we can't find the slope of this graph right at 4 seconds is we get division by 0 when we do that. So our process is to do what we just discussed, right? We're going to let the 2 points get really, really close together. And this is a limiting process. So if we scroll back up for just a second in our table, we can see what's happening with the denominator, right? Our delta x, if you will. These values go to 0. Right, my delta t is going to 0. And what that tells me then is that my average velocity, or I should just say my velocity, it's not becoming average anymore, right? It's becoming an actual velocity. Right? So my velocity is approaching, it looks like, -8 feet per second. Okay, so in this application, what we're doing is we're exploring this limiting process. And by looking at an application where we're using slopes that produce a rate of change of feet per second. Now, if we think for a second away from this application of dropping an object out of a tree, there are lots of different rates of change that exist in the world. So feet per second is one of them, right? Speed or velocity. We can also measure velocity or speed as miles per hour, or for the metric system, right? Kilometers per minute or kilometers per hour. Let's see. We could also think of, let's say we have a tank of water, and as we begin to drain the water out of the tank, we could look at the rate of change. The height of that water, right? The amount of water in that tank is changing once I pull the plug on that tank. So we could have gallons per minute or gallons per second as that rate of change. We could look at how temperature varies over the course of a day. So if we're measuring temperature in degrees Fahrenheit, right, as time progresses through the day, we could look at degrees per hour as the rate of change of our temperature over the course of a day. We could also even look at how the flow of electricity, the current flow through a circuit. And we could talk about the charge flowing through that circuit over time, let's say. Right? So anyway, there are a bunch of applications of rates of change within the real world. And what we have explored in this example is how that might look in a particular scenario where we're looking at a speed, right, or a velocity. So we're dropping an object, and the height of that object is measured in feet, and then that height is a function of time. So we know that after 1 second, the object has moved, after 2 seconds, after 3, after 4, and so on. All right, and if we look at this graphically for a moment, I've brought up the graphing calculator Desmos.com, and I'm going to try to visualize in a little prettier manner than I was able to in my Word document. Right? So I tried to show that this point slides down to the point t equals 4, and I'm going to use Desmos just to make that look a little prettier, kind of animated. So here's the point at t equals 4. I've started at t equals 0 seconds, right at the height of the tree. And what we did in that table, so we grabbed that point and we slid it closer and closer and closer together. And we can see that awesome secant line, right, is becoming more and more like the slope of the graph. So again, when I look at the average rate of change here, I can see the line isn't the best estimator of the curved parabola. But as I bring these points closer together, notice how this line is becoming more indistinguishable from that parabola. And as it gets closer and closer, we can see the line becomes much more of a better estimator of the parabola between these two values. Right? So we could see that in this limit process here, as those 2 points got closer and closer together, we could see the slopes becoming -8. Now again, within the context of this word problem, we're looking at feet per second as the unit of that limiting process. All right, so what I want to do now to finish off this conversation is I want to look at this concept in a little bit more of a algebraic manner, if you will. So let me go ahead and draw another picture of a graph. Now, I'm going to exaggerate the shape of this graph here, right? So I'm gonna kind of look at this as my graph. This is some function f of x, let's say. So this is any function, right? And that is one sloppy f. Let me fix that. So we have any function here, right? So let's say we're wanting to find the slope of the tangent right here. We're going to look at x equals a. So let's say we have x, and we have our function values here. So I'm going to slide the point backwards, right? So I'm going to move some distance away here. Let's call this a plus h. So I'm moving some distance of h away. So I'm looking from this point to this point. So I'm just going to go a little backwards, right? I'm going to slide the point in this direction. Okay? I'm still going to give me the same result ultimately. So what I'm doing, again, is I'm finding the rate of change between these 2 points. And again, that's the slope of the secant line. Right? So our average rate of change, our slope of our secant line, our average rate of change is going to be, the change in y over the change in x. Now, in particular, I need to know the y values and the x values. So if you think about it, whatever my function here is, the y value is plugging this x value into the equation. So I'm going to take a plus h, I'm going to plug it into that equation, and I'm going to get f at a plus h. So whatever that x value is, whatever this x value is, I plug into the function and get f at a plus h. And then I'm going to subtract this y value. And again, the value of x that I'm plugging in is a, so this y value is f at a. So there's that y value at that point. And then technically the distance between these here is the difference between them two. So a plus h minus a is really just going to give me h, right? That is my delta x. The distance from here to here is h. So I'm just going to write h. So there's the slope of the secant line. That is my average rate of change. Now what we did in the prior problem is we started here, right? And we found the slope between these 2 points. And we numerically picked points closer and closer and closer and closer. Right? So we went, from 1 to 4, 2 to 4, 3 to 4, 3.5 to 4, 3.99 to 4, so on and so forth. So in other words, as these 2 points slide closer and closer together, what we're doing is we're letting h get smaller and smaller. So I want h to get here, and I want the point to get here, and the point to get here. So we're letting h go to 0 is what we're doing. So we're going to call that the instantaneous rate of change. So what that means, right, in the context of a word problem is we're not finding an average speed anymore, we're finding an instantaneous speed. So instead of from 3 to 4 seconds, we want to find the speed at exactly 4 seconds. So bam, right at 4 seconds. When we want to find right on that instant of time of 4 seconds, we want to find the speed or the velocity of that object that was falling. So we're no longer finding an average between 2 points, we're finding the slope, the instantaneous slope right at one particular point. So what we did in that table is we used the limit process. So this instantaneous rate of change is going to be the limit as h goes to 0 of this exact same slope. So again, we want the h to go to 0. We want this to get smaller and smaller because this point will slide to this point. As this point slides to this point, the h is going to 0. So Within the formal context of average rate of change and instantaneous rate of change, for any function that we look at, the average rate of change is what you might call a difference quotient, right? So usually in a pre-calculus class, this is called the difference quotient. And then within this context, we want to not only find the average, we want to find the instantaneous. So we have to put this limit process into that problem. Now, when we look back at the example that we just did, we look at that table, we saw that limit process produce -8. So again, in our table, here is our h going to 0. Right? So our denominator, we called the change in time, right? But our denominator of our slope went to 0. So again, in this application, as that term went to 0, in that particular application, we got -8 as that limiting process. And again, I want to point out to you here's the really cool thing about a limit. So when we get to the 2 points lying on top of each other, right? When we have the 2 points lying on top of each other from 4 to 4, we get a division by 0, and that's undefined. Well, here's the beauty of the limit. We're never really going to get to have the points be exactly the same. We're never going to get to an h of 0. We're going to let it approach closer and closer and closer and closer and closer and closer and closer, as close as we want to get. We could have gone from 3.999999999 to 4, right? We could get really, really close, but we're never going to get there. We're never going to let the 2 points become exactly the same, and that's the beauty of the limit. So again, we pointed out to ourselves that when we look at the instantaneous slope and we try to calculate that with classical rise over run, we get an undefined value. But physically, we could see there was a measurable slope to this graph. So the limit process allows us to explore, to discover what that slope wants to be. And that's the whole concept of the limit. The limit allows us to see what the average wants to become to be instantaneous. Okay, so let's see what this looks like back in context of that word problem we just looked at. So back in that word problem we just looked at, right, we were finding the slope at 4 seconds. Right? So what I'm going to do then is let's plug into this instantaneous rate of change formula. So what I'm doing for this particular rate of change is I'm finding the slope of the tangent line at 4 seconds. So I'm going from 4 seconds, I'm moving away from 4 seconds, and I'm letting this go to 0. So we're looking at the slope of that tangent at 4 seconds. Right? So here's what we're doing in the context of our word problem. Now, in our word problem, keep in mind I used the letter h, right? But we had f of t being 16 minus t squared for that problem. Again, I used h of t there, but bear with me. Forgive me for switching to f. Right? So what I'm going to do in that case is I'm going to plug this value, right? This is my x value, into my function. So I'm going to take 4 plus h, and I'm going to plug it into this function. So I'm going to have in the numerator 16 minus 4 plus h squared. So let's say that's this value here. I'm going to close that in brackets, and then I'm going to subtract f at 4. So I'm going to plug 4 into here. I'm going to get 16 minus 4 squared. Now, all of that is over h, and we're looking at the limit as h goes to 0. All right, now what we've got to do is a little bit of an algebra process here. So in other words, I'm going to take this numerator and I'm going to FOIL, I'm going to multiply out this expression, and I'm going to clean all of this stuff up. So bear with me for a second. I'm going to do a little bit of, let's call it algebra side work, and I'm going to clean up that numerator. I just want to do that on its own. I don't want to have to carry all of that cleanup through and bring the whole fraction with me. So let's do a little bit of algebra side work. So I got 16 minus, and then keep in mind this is h plus 4 times h plus 4, algebraically speaking. And then I have minus, this is 16 minus 16, which is 0. Right? So when I FOIL this expression out, right, I'm going to get h squared plus 4h plus 4h plus 16. Oops, I got 16 minus all of that stuff, minus 0. So this is going to become negative h squared when I distribute. This is going to become, so this is 8h, so this is going to become minus 8h. And then I'm going to have negative 16 plus 16, that's going to cancel. So here's my expression in the numerator when I've simplified. So I'm going to come back up here. This whole numerator, my fraction up here, has become negative h squared minus 8h. So I'm going to rewrite this expression with the limit process. So back to my limit, right? I'm done with my side work. I have the limit as h goes to 0, and I have negative h squared minus 8h all over h. Now what we're doing here, I could build a table of values. And I could let h go to 0. So I could start with this expression, plug in h equals 1, and then I could plug in h equals 0.5, I could plug in h equals 0.1, h equals 0.01, and then 0.001. I could let h go to 0. Now I'm going to go ahead and clean this up for just a moment. I'm going to factor in h out of the numerator. And notice that's going to reduce with the denominator. So I have the limit as h goes to 0 of negative h minus 8. Now again, instead of having to build a whole entire table to explore this, right, if I plug in h equals 1, I'm going to get, excuse me, then h equals 0.5, h equals 0.1, h equals 0.01, 0.001, 0.0001, right? So when this becomes 0, I'm going to have 0 here, and I'm going to get negative 8 as my end result. And that was exactly what we saw in the table. So when we took the time to construct that table, let those 2 points become the same, we saw the average rate of change becoming the instantaneous rate of change right at t equals 4. All right, now I've opened up the expressions that we typed in Desmos. I'm going to point out to you, right, here's the slopes of all my secant lines. So as I grab this point and let it get closer and closer to 0, look how these slopes are changing dynamically. And notice how they're getting closer and closer to negative 8, as we already know they're going to, right? So that is what we've done algebraically here. So instead of having to build a table to explore a whole bunch of different values, we've done this in an algebraic manner. Okay, so again, just in summary, right, when we took 2 points that were a distance h away, that gave me an average rate of change. The slope of that secant line was the average rate of change. We want these 2 points to become the same, or at least approach that process. So the instantaneous rate of change provides that limiting process. We let those 2 points slide together. So the h goes to 0, sliding those 2 points together. For this particular example, here was my function where I plugged in a plus h and a, right? So I had 4 plus h and 4 as my points got closer together for that parabola. And we saw that process lead to the same thing we got in the table of negative 8. That is so cool. All right, so the beauty here, right, is that limit process. That limit process really makes this doable. It makes us explore what would happen when the 2 points become the same, if that were to happen. So as the delta x went to 0, as those 2 points got closer and closer, we see what the instantaneous rate of change would be. Now again, I want to summarize for a moment here, right? And we've used a couple terms in particular that were kind of interchangeable. So we were talking about an average rate of change, and graphically speaking, we called that the slope of the secant line. Now we talked about that slope, being delta y over delta x, let's say, right? So this was the slope between any 2 points. Then we talked about the instantaneous rate of change. I'm going to get lazy. Rate of change, right? So the instantaneous rate of change, we called that the slope of the tangent line. So the tangent line basically being a line that touches the graph only at 1 point. So instead of looking at an average over 2 points, we looked at the slope at specifically 1 point. And what that involved was the limit process. So we had the limit of our slopes of lines. And the way that I've written this, right, the x's have to go to 0. The delta x has to go to 0. So I'm going to say delta x goes to 0 the way that I have written this expression. Remember, the formula that we wrote was that this would be the limit as h goes to 0 of f at a plus h minus f at a all over h. And again, referencing that picture we drew up on that prior page. Now, this is all wonderful when we have an equation. So we had an equation of 16 minus x squared within the context of that, dropping the stick. But what if we don't have an equation? What if we only have a table of data? How would we handle this process if we only had a table of data? All right, let's take a look at this one last scenario. So when I don't have an equation, how would I take this approach of using average rates of change to estimate instantaneous rates of change? So here we have a scenario where we have a tank that holds 1,000 gallons of water, and it drains from the bottom of the tank in half an hour. So the values in the table show the volume of water remaining in the tank after t minutes. So we made measurements. Looks like we've made measurements every 5 minutes. So at t equals 0 minutes, we had 1,000 gallons. At 5 minutes, we've dropped to 694. After 10 minutes, 444, and so on and so forth. So let's say we want to focus on 15 minutes. So let's say we want to find what's the instantaneous rate of change at 15 minutes. So let's say, what is the instantaneous rate of change at 15 minutes? Okay, so there's a couple of ways for us to do this. Right? One way would be to say back off to the left, and we're going to find the average rate of change here. So that could estimate possibly the instantaneous rate of change at 15. So let's say we look at the average. Let's look at the average from 10 to 15 minutes. Right? So again, the average rate of change, I'm going to say average rate of change is going to be in this case, it's our change in y value. So we're going to have the change in volumes over the change in times. Right? So if this is my, final and this is my initial, I have 15 minus 10. Oops, I am so sorry. That is my time unit, not my volume unit. So I have 15 minus 10 as my time units, and then I have 250 minus 444. And if we plug all of that into a calculator, we get negative 38.8. I'm going to say negative 38.8. And then what would be our units on this expression, right? So remember, the volume is being given to me in gallons, and the time is being given to me in minutes. So I'm going to have gallons per minute as the unit for my rate of change, right? So again, how are we interpreting this? Well, what we're saying is, as the tank drains, right, the average rate of change from 10 to 15 minutes is 38.8 gallons per minute. And again, the negative here is going to denote the decrease. So the volume is decreasing as the water drains. So just like in our example, we had negative 8 feet per second, what we dropped out of the tree. So the negative shows me the direction that the height is decreasing. So now let's go ahead then and let's estimate the slope. Let's find the average rate of change between these two values, right? So I'm going to take this as the final at 20 minutes and subtract the 15. All right, so let me scroll here a little bit and let's see what that looks like, right? So we're going to follow the same process. So let me change language a little bit here. So I'm going to say the average rate of change over the interval from 15 to 20 minutes. So that average rate of change Again, we're going to have the change in velocity over the change in time. So we're going to have change in velocity of 111 minus 250 in my numerator. And then we're going to have the change in time of 20 minus 15 minutes. Taking out a calculator to find that value, we get negative 27.8. And again, that's going to be, gallons per minute. Okay, so I'm going to draw a graph here which doesn't necessarily represent that data set. So if I draw a graph here, let's pretend, it's a parabola, but it's not necessarily, right? So let's say we have a parabola. So what we did was, let's say here was 15 minutes, right? We backed away and we did 10 to 15 minutes. And then we jumped forward and we went from 20 to 15 minutes. And we found those two secant lines, the slopes of those secant lines. But something we could do to be a little bit more precise is we could average these two values. So we're in essence finding the slope of the secants between those two values, in essence. So we're going to average the two rates of change that we just got, right? So a little bit more of a precise measurement. So let's say the instantaneous rate of change, what we will do is we will average, right? We'll average the two from the two sides. Right? So in this case, we're going to average those two values that we got. So what were those two values that we got here? Let me scroll back up and let's see. So we had 38.8 and 27.8. So we had 38.8 and 27.8. We're going to average those two values. Now remember, this tank is draining, so whatever we get out of that value, it's really a negative measurement. And we get 33.3 gallons per minute. All right, so in this example, what we looked at and what we considered was a rate of change where we don't have an equation, we just have numerical data. So how might we approach that? So without that formula, right, for finding the average rate of change to an instant rate of change, we use the limit process. Can't really use the limit process here because we have a finite set of numerical data. We only had a couple specific points in our data set. So again, we used a couple different estimations. We went from 10 to 15 minutes and we got an estimation there, right? The average rate of change estimates the instantaneous at 15, and then we went from 15 to 20, and again that average rate of change estimates the instantaneous rate of change at 15, and then we realized that if we average these two values, we're going to get a little bit more accurate of an estimation of the instantaneous rate of change right at 15. All right, that's everything I wanted to discuss with you here in this video. And what we'll do in the next video is we'll take that concept of a limit and we'll take it a little bit deeper. So we will formalize what a limit is, how we would officially do limits for other types of functions. So we focused on limits specifically taking an rate of change, right, a difference quotient. We're going to look at all different types of functions in that next video.